So there's a lot of writing on the board. I want to focus up here to start. So it would be really convenient if we could algebraically evaluate whether or not a critical point is a max value or a min value. And it turns out we have a second derivative test that will help us do that. The second derivative test is much more complicated than the second derivative test that we saw for single variable functions. And I'm going to walk through what exactly this second derivative test is telling us. So the first step that we need to do is we need to evaluate something that's called the discriminant. So we start with this Hessian matrix. Now, you don't have to memorize this if you don't want, but I think that this is a helpful way to remember what the discriminant is. So let's say that I have a Hessian matrix. This matrix is a matrix of all of the partial derivatives. So I have the second partial derivative with respect to x, and the second partial derivative with respect to y along the main axis, and then the mixed partial derivatives along the minor axis. And it turns out that if I take the determinant of this matrix, and the determinant of this matrix is going to be the major axes multiplied together, f sub xx times f sub yy, minus f sub xy times f sub yx. This thing right here we call the discriminant, and we label it with a capital D. Notice that a shorter way to remember it is that these mixed partials, by Clairaut's theorem, the partial with respect to x and then y is going to be equal to the partial with respect to y and then x. And so I can rewrite this, if I wanted to, as the second derivative with respect to x, the second derivative with respect to y, minus the mixed partial derivative, mixed because it's x and y, squared. So this is what we call our determinant. This is our d value. And we need this in order to be able to compute the rest of our second derivative test. So once I've found this discriminant, I can use my test. And there are 4 different cases. So let's say that AB is a critical point, because that's what I'm trying to test. I have a critical point. I want to know whether it's a max or a min value. So if my discriminant is positive, and the second derivative with respect to x is negative, then AB is a max. You need to have both these criteria in order for my point AB to be a max. Similarly, if my discriminant is positive, but my second derivative with respect to x is negative, then the second derivative with respect to x is positive, it's greater than 0, then AB is a minimum value. I'm going to highlight something here, that this little piece right here and this little piece right here are exactly what we saw in the one-dimensional case. Remember that if my second derivative is negative, that means my acceleration is negative, I'm being pulled downward, and that means that my point is at the top of that peak. And if my second derivative is positive, I'm being pulled upward, and my point is going to be at the bottom of that valley. So these are 2 things that you already know from previous calculus work that you don't really have to memorize. And these are the 2 cases, the cool cases, and they only happen when my discriminant is positive. What about if our discriminant isn't positive? We have 2 more cases. If my discriminant is negative, then I don't have to do any more second checks with second partial derivatives. If my discriminant is negative, then I know that my point AB is a saddle point, and I'm done. That's it. Finally, we have a discriminant that's positive or negative in previous cases. What happens if my discriminant is exactly equal to 0? That tells me that my test is inconclusive. It actually turns out that if the determinant of this Hessian matrix is equal to 0, it means that this is a non-invertible matrix. I'm not going to get into a lot of theory, but essentially, we would have to graph it. That's the tool that we have. If it turns out that our discriminant is 0, the tool that we have to be able to evaluate max and mins at that point is just to look at a graphical display. So let's use the second derivative test to be able to evaluate the maximum and minimum values of this function. This function is given by x squared plus 4y squared minus 2x squared y plus 4. So how do we find critical points? Let's take partial derivatives. So my partial derivative with respect to x is given by 2x minus 4xy. I believe that's correct. And I want to know I know that this is continuous, each of the pieces are continuous, so I want to see when is this function equal to 0. I can factor out my x, and I get x times 2 minus 4y. So this is going to be equal to 0 either if x is equal to 0, and I'm recording this in my little chart over here, or if this interior part is equal to 0, and that happens, I can solve this algebra in my head when y equals 1/2. Let me go ahead and solve that. That's when 2 is equal to 4y and y is equal to 1/2. So my partial derivative with respect to x, there are two different ways that this partial derivative could be equal to 0, and these are the two possible ways. But in order to be a critical point, it means that both the partial derivative with respect to x and the partial derivative with respect to y have to be equal to 0. So let's continue on by finding the partial derivative with respect to y, which in this case is 8y minus 2x squared. And I'm going to set this equal to 0 because both my partials have to be equal to 0. And I can move my x squared to this side, and I can divide both sides by 2, and I get 4y is equal to x squared. So let's use the information that we had from these points to plug into this function to find out, well, if the partial derivative with respect to x has to be equal to 0, that happens when x is equal to 0. When x is equal to 0, that means that y would also have to be equal to 0. So I'm going to plug in this x equals 0 into this function, and what do I get? I get that x was equal to 0 and y is also equal to 0. So I know that that's one of my critical points. Similarly, I'm going to plug in y equals 1/2 into this function and see what I get out. So I get 4 times 1/2 is equal to x squared, plugging in this y value. And I see that 4 divided by 2 is 2 equals x squared, which means x is equal to the square root of 2, both positive and negative. I took the square roots. So what is this saying? This is saying that if y equals 1/2, then in order for both of these partial derivatives to be equal to 0, we would have x having to be equal to square root 2, or x being equal to negative square root 2. So that gives me two more critical points. Square root 2 1/2 and negative square root 2 1/2. And these are the only places that we found for which both the partial with respect to x and the partial with respect to y would be equal to 0. So we found all of the critical points. After we found the critical points, we're now going to use our second derivative test. Ooh, I'm not going to erase everything. We're going to use our second derivative test to be able to determine whether these points are maximum values or minimum values. So recall, for our second derivative test, we're going to need a number of pieces. We need to have the discriminant first. So I'm going to compute the discriminant. I'm just going to recopy this up here to try to save some space. So we've already found our partial with respect to x and our partial with respect to y, but we need a few more pieces. We need our second partial derivative with respect to x. So I'm taking the derivative of this, and I get 2 minus 4y. We also need the second partial derivative with respect to y. So I take the derivative of this with respect to y, which is just 8. And we also need our mixed partial, the derivative with respect to x and then y. And so I'm looking at my partial with respect to x, which is up here. And then I take the derivative with respect to y, which in this case is just this coefficient negative 4x. Similarly, I could have done this by taking this function and taking the derivative with respect to x, which agrees it's also negative 4x. So now we've come up with our discriminant. Our discriminant in this case is going to be, recall, it's given by the second derivative with respect to x, the second derivative with respect to y, minus the mixed partials squared, which in this case, my second derivative with respect to x is given by 2 minus 4y. My second derivative with respect to y is 8. And my mixed partial minus my negative 4x squared, I can simplify this. I end up with 16 minus 32y, 4x squared becomes minus 16x squared. So this is my discriminant. That doesn't look like it's positive or negative. It's because I haven't evaluated it at each of these points. So now we have 3 final steps where I'm going to evaluate the discriminant at each of these points. So my first step, I wish I had a little more space on the board, but I don't. So I'm going to erase this again. My first step is I'm going to evaluate my discriminant at my first critical point given by 0, 0, where I plug 0 in for x and 0 in for y, and I see that it's equal to 16. Great! Equaling 16 means that my discriminant is greater than 0, which means that it's either a max or a min, but I have to do one more test to be able to find out whether it's actually a max or a min. So I have to plug my point 0, 0 into my second derivative with respect to x. And recall, my second derivative with respect to x is given by 2 minus 4y, which is equal to 2. So we just found that our discriminant is bigger than 0, and our second derivative with respect to x at 0, 0 is it's greater than 0. So that means that our 0, 0 point is a min. Second derivative with respect to x being equal to 0 means that 0, 0 is a min. Nice. So we evaluated one of the points. Let's go ahead and evaluate the final 2. Our discriminant at square root 2 1/2 is going to be given by 16 minus 32 times a half is 16, minus 16 times x squared is 2, times 16 becomes 32. So 16 minus 16 is 0, minus 32. This is less than 0. I don't have to do a second check here. I know that if my discriminant is less than 0, then I have a saddle point. So without doing any extra work, I know that my second critical point we found to be a saddle because my discriminant was less than 0. And then finally, I'm going to check my third and final point. Oh, but it ends up being really similar. Look, it's going to be 16 minus 32 times a half is still 16, minus 16 times x squared. Well, my x coordinate is negative square root 2, so it's going to be minus 16 times 2, which is the same thing that we got before. So this is equal to negative 32, which is still less than 0. So it still means that this point is a saddle point. Phew! So maybe you're tired of all of this work. It turns out that this algebraic process isn't that complicated. It's just a little algebraically tedious. The steps that we did, we started with this function. First, we found the critical points by setting our partial derivatives equal to 0. Then we used our second derivative test to find out whether our critical points were maxes, mins, or saddles.